All right, so in this problem we have an Atwood machine. So you remember from first semester, an Atwood machine is simply two masses connected over a pulley. However, in first semester, what we did is we called the pulley massless. I don't know if you remember that. I think I told you guys we're not going to worry about the pulley. We're just going to say it's a frictionless, massless pulley. And if that were the case, if the pulley had no mass to it, that means the tension on each side would be equal. The tension here and the tension there equal if the pulley has no mass. Now, if this pulley does have a mass, which it does in this problem, would it take a torque, a net torque, to get it accelerating? Yeah, because look, if these two tensions were equal, would that pulley start to accelerate? Or would the torques just cancel? The torques would just cancel. So if this pulley has a mass and therefore rotational inertia, which of these two tensions, so let's call this T1, we'll call this one T2, which tension has to be larger in order to make the pulley start to accelerate clockwise? Which of the two tensions would have to be bigger? T2. Okay, so the torques are not equal here. Okay, so we're going to start by setting this up. So here's the text here. So we're finding the acceleration of the 0.5 kilogram mass. And by the way, the acceleration of this guy and the acceleration of this guy, same or different? Same, but if you read the problem, it makes it sound like the acceleration of this guy is different than the acceleration of the other guy. The two masses have the same acceleration because they're connected by a string. Okay, then we're going to find the angular acceleration of the pulley and then the rotational inertia of the pulley, which is the hardest part. Part C takes the most time. All right, so let's start this. So we're going to begin with a free body diagram. Okay, in fact, let me shrink this down. Okay, so I'm going to call the mass on the left is going to be M1. This. So this guy is M1, this guy's M2. So the forces on M1, we'll call this T1. And then down we have M1G. Okay, for M2, we have T2 up and then M2G down. I'll scoot these guys down, make a little more room. That. Okay, now the forces on the pulley. What's pulling on this side of the pulley? T1. On this side of the pulley, it's T2. And they're not the same tensions because it's not a massless pulley. All right, we are told in the problem that M2 it comes down. So X here is 0.75 meters. So 0.75 meters in a time of 5 seconds with an initial velocity of 0 meter per second. So the first question can be solved with a kinematic. You just go X equals 1/2 AT squared. The most commonly used kinematic, V initial is 0. So the acceleration of M2 as it comes down must be equal to 2x over t squared. So that's going to be 2 times 0.75 meters over 5 seconds squared. And then this gives an acceleration of 0.06 meter per second squared. Okay, that's part A. Now, part B, the angular acceleration of the pulley. So there's an equation that we can use to get that. So here's the idea, guys. In fact, look, I want to talk about this for just one brief moment. Look, so let's say here's the pulley. So this pulley is going to accelerate, right? So if you look at a point on the wheel here, so let's say it starts to rotate like this. Will a point on the wheel have what we call a tangential velocity? So imagine a speck of dirt. The speck of dirt on the pulley flies off. How does the speck of dirt leave the pulley? Tangent to the circular path that it was in. Now, does the tangential velocity change as the angular velocity changes? So this pulley has an angular velocity. What's happening to the angular velocity? It's getting bigger, bigger, bigger because the pulley's going faster, faster, faster. So as the angular velocity increases, the tangential velocity increases. So like for example right here, the tangential velocity is going to be larger. So that's supposed to be a larger vector. So like, let's say here it's like 0.1 meter per second, and then here it's 0.2 meter per second. So guys, we had an angular acceleration, which caused the angular velocity to increase. And if the angular velocity increases, what happens to the tangential velocity? It also increases. So we have what's called a tangential acceleration. So look, to solve part B, a point on the perimeter of the pulley has a tangential acceleration, and you can say that that tangential acceleration is equal to the angular acceleration times the radius. It's the same logic as, so we talked about this equation, tangential velocity is angular velocity times radius. If you want tangential velocity, take the angular velocity multiplied by the radius. If you want tangential acceleration, take the angular acceleration times the radius. And what has to be true for these guys? The angular velocity and the angular acceleration has to be in radians. Okay, so the way we're going to do part B, it's a very quick calculation. So part B, we just go like this. So focusing on a point on the perimeter of the wheel, the tangential acceleration equals the angular acceleration times the radius. The angular acceleration is going to be the linear acceleration over the radius. We already know, we know what the linear acceleration is. It's the same as what the acceleration was for that. Okay, so this is going to be 0.06 meter per second squared. The radius of the pulley is 0.05 meters. So this gives an angular acceleration of 1.2 radian per second squared. All right. Now, the last question is the most time-consuming question. Finding the rotational inertia of the pulley. So to do this, what we're going to do is so we're on part C, we're going to focus on M1. What are we going to do for M1? For this guy here, what can we do? Sum the forces. So summing the forces, we're going to say T1 minus M1G equals M1A. Okay, then we're going to go to M2. Over here. Now guys, sign convention rounds the pulley. For M1, up is positive, down is negative. That sign convention goes up and over the pulley. So then over here we have down plus, up minus. Basically the direction of the acceleration is positive. M1 accelerates up, so that's positive. M2 accelerates down, so that's positive. Sign convention wraps the pulley. So summing the forces for M2, we're going to get M2G minus T2 equals M2A. And then the last thing we're going to do is we're going to focus on the pulley. What can we say for the pulley? We can sum the torques. Okay, so looking at the pulley, how many torques are acting on the pulley? 2. So what's going to be the torque from T2? T2 times, what's the perpendicular distance from the axis? R. From the axis over to T2 is the radius. Okay, then T1 is going to be minus, because that's in the other direction, right? Clockwise, counterclockwise. T1 times R, those are the two torques. what is the sum of the torques always equal to? I alpha. All right, at this point, the rest of the problem is simply algebra. Okay, what are we trying to solve for here? The question wants us to find the rotational inertia. We're looking for this. Thanks. So you take this equation, solve this equation for what? T1. T1 comes out as 4.5356. Oh, and you know what, guys? For this problem, use gravity as 9.8. Because look, our acceleration here is 0.06. You're plugging that in for A. That's a very small acceleration. So use gravity as 9.8. Okay, you solve this for T2. T2 comes out as 4.87. Okay, then take T1, plug it in there. Take T2, plug it in there. Take this, solve it for I, and you get 0.014 kilogram meter squared.